Finally, we proceed to prove that CFLs are closed under inverse homomorphism. So what was inverse homomorphism? Again, we discussed it when we discussed regular language. It's the same here. So we just defined homomorphism. So homomorphism is this map. And inverse homomorphism is just the inverse map. Like you define inverse of any map in mathematics, right? So homomorphism was this mapping string from over this sigma to strings of delta. So the inverse of this thing is the set of all strings such that any string here it maps to this W. So the inverse is a set, okay, and inverse of this whole language L is then any string x such that h of x is in L. So it's the normal definition of inverse of any map, right? So now since this H satisfies this relation, this homomorphism, and in particular if I break this down into individual symbols, then H of A1 up to AN is H of A1 concatenated up to H of AN. So this means that suppose for this AI here we have HAI as WI. So this is a string over delta, right? Because of this. So this may contain multiple symbol over delta. So if I have this, so then it means that this string, so W1 concatenated up to Wn, will be in L if and only if this A1 up to AN is in H inverse of L, right? So this will be, so that is why there's a vice versa with this if then. So this is what H inverse of L is, right? Because if you have something in H inverse of L, then if you apply H, so H of this thing will be this thing, which is concatenation of this, that will be in L. Okay. So now if we want to prove that if L is a CFL, then H inverse of L is a CFL. So if we want to prove that, so then we first suppose that there is a PDA M which accepts L via empty string or via empty stack or via final state, doesn't matter. So what we will do is we will simulate the moves of this PDA of L, not simulate the moves. We kind of take the moves from here, and correspondingly we construct another PDA which makes moves over this string. So you will see in the proof that it really doesn't matter whether this PDA is accepting this L via empty stack or via final state, but for the sake of the proof, let's say it accepts this L via final state. Okay. So PDA for L, so this we say by final state. By final state. By finals. Okay. So then our goal is to construct a PDA for H inverse of L. Now, what should be the relationship between these two PDA? So see, suppose this PDA is processing this string, okay? Suppose it's processing this string, and it has processed okay, not this string, this string, because it is concatenation of this one, okay? So each HAI is some WI, so it's processing this computation of this thing. So and suppose it has processed up to some HI minus 1. Okay, it has processed up to some point HI minus 1, and from this HI we have the remaining string here, and at this stage the state is say Q, okay, and the stack is alpha. So this entire thing is a ID of M, right? So then after some steps, more than one steps, so that is why we have star, and in M, okay, so this ID transform into this ID where it has completely consumed this part, okay, this part of the input. So this HI is now gone, so it starts from this HI plus 1, so the remaining part is HI plus 1 up to H of AN. And then the stack has changed into something beta, which depends on how we replace the top symbols of stack, right? So this means this sort of argument we gave before. So this means that if we start from Q and if we just process H of AI, forget about the remaining part here. So if we just process AI and with this stack alpha, so then we will reach this ID where the state is P, and this part is entirely consumed, so this has become epsilon, and then the stack becomes beta. So we will have this. So there's a one-to-one correspondence between this chain of transition and this chain of transition, right? So let's just focus on this. It's simpler than just mentioning this, the remaining part. So suppose this is happening in M. So the corresponding thing that we want in M prime is that it should just consume this AI, okay? Because you see, in L, if we process W1 up to Wn, I mean that means this HA1 up to HAN, correspondingly we should process this A1 up to AN in H inverse of L, right? So this should be accepted, if this is accepted. And we are kind of just simulating it in a way that when it processes this part, it should be equivalent to processing just this one symbol here. So again here, since we started with this H of AI, so that means it has already processed some prefix of this whole thing, and after that it starts with AI, and then it processes this AI. It may take multiple steps. Why multiple steps? Because okay, it can consume this one symbol and then it can take epsilon transitions also, right? So there can be multiple transitions, including epsilon transitions, which does not read any more symbol. But after that, this part is remaining. So that means only AI is consumed here, and it also starts with this state Q. Okay, so we will construct it in such a way that the states here include all the states here. So there will be extra states here, we will see later, but at least it has all the states that are here. So it starts with this state Q and the same this stack alpha, and after just consuming this AI, it goes into state P and stack beta, same as this one, but instead of consuming HAI, it just consumes AI. So again, it is equivalent to saying that it just consumes AI. So instead of taking this long thing, you say just it starts with Q, process AI with stack alpha, and then it finally reaches this state P, where it has consumed this thing, this string with just one symbol, and the stack is beta. Okay. So this is what we want, where we have this in M, right? So as I said, this HAI, so this is a string over this alphabet, this lambda, right? So H of A, if you consider any AI here. So this is, so let's just say this is A, just for convenience. So this is concatenation of multiple symbols, okay? So all this BJs here, so all these BJs here are coming from this delta. Okay, so this delta, so it's a symbol in delta. So we have a string here over delta, and starting from state q, it processes all these symbols here, and it reaches p and stack beta. So this should happen if and only if this happens, okay, in m prime that we are supposed to construct. So this is our motivation for defining m prime. We should define m prime so that it satisfies this criteria, and if it satisfies this criteria, then we know that m prime is a PDA for h prime L. Okay, so is that clear? So we have reduced our problem of constructing h, of showing h inverse L is a CFL to this problem that this m, the PDA m for L is given, and we must construct a PDA m prime which includes the states of m, which shows this behavior that if this chain of transition occurs in m, so then there should be some chain of transition in m prime which consumes a and does this. So the correspondence is between a and h of a. H of a is this whole big thing where each of the symbols are here. Okay, so now let's just proceed to show how we can do that. So yeah, so this is what now we should prove. Okay, this statement we have reduced. So let's just consider what happens with this string in m. So m is given, right? So it starts with the state q. We'll just call this q1 for convenience. So it's a first step. So we are just giving it another name. It's not different state. And similarly, this alpha, just call this alpha 1. Okay. So then, okay, so this should be just, this should not be star. So this we can say it's just a single, yeah, so this is, this star should not be there. So these are just single step process, okay? So we can ignore the stars. Or maybe you can keep the stars here if you consider epsilon transition here also, okay? So maybe in that sense you can keep the stars, but anyway, these are consuming just one symbol. So that is what I'm saying. Okay. And by the way, without loss of generality, you can assume that this L that we are talking about is epsilon free. We can always do that, and then later we can introduce this epsilon, because epsilon is mapped to epsilon under homomorphism, under any homomorphism. So to keep things simple, we can assume that L is epsilon free. So then we can construct a PDA for L which does not have epsilon transition, so that we can do because of this GNA. You remember, for any CFL we considered the GNF form of grammar which accepts that L, and from that GNF we constructed the PDA. So if you see the proof where we prove that every CFL is accepted by some PDA, so we use a grammar in Grayback normal form, and that ensures that if this L is epsilon free, then there is no epsilon transition. So here we can even ignore the epsilon transition. So we do not really need this stars. Okay, so then what happens? So it consumes this one symbol, and then it does something to the stack. So it just replaces the top symbol of this alpha 1, right? So that means the leftmost symbol of alpha 1 is replaced by something, right? So then this b1 is gone and the stack becomes something, and then it moves to some state q2. Similarly, in the next step, it will consume this b2. So this q2 will be transformed into something, say q3, and then the leftmost symbol of alpha 2 will be replaced by something, some gamma, right? So it will be some alpha 3. So in that fashion, it will keep on consuming this B1, then B2, then B3, and then finally it will come to this point where it has only one symbol, and then it will make another move where we reach some QK plus 1. So everything here is consumed, and the stack is some alpha k plus 1, which we call beta because we have taken beta here. So it's just another name for this beta. Okay, and this is just another name for this P. So this is what happens in in M, which accepts L, right? This is for M and L. So correspondingly, we need some transitions in M prime, which can now do this. So instead of consuming this whole thing, which is H of A, so which is H of A, so it will just consume this single thing A, and it will also move from Q to P, and the stack will move from transform from alpha to beta, right? So this is what we have here in M prime. Starts with QA alpha, and finally it reaches this P epsilon and beta. So now then, what kind of transitions should we have in M prime? Now see, since it just is supposed to consume this one symbol, so in one move you can consume this one symbol. Rest of the moves has to be epsilon if there is any other move, right? And this is what we will do. So the very first step we will that it takes. So we will design the transitions accordingly. We haven't specified what the transitions are. So here we are just kind of figuring out what kind of transitions we need for this M prime, right? So our plan is to just first consume this A, okay, in M prime. So again, here these things are just single step thing. So we do not need the stars here, okay. These stars are not required. It's a single step thing. So so in the first step, it just consumes this A, and it makes the same changes on the stack. So whatever substitution it makes to the leftmost symbol of alpha, it makes the same substitution here. So it goes to the same, here it doesn't make any change. So this point onward it makes change, because from here alpha 1 to this we have just this alpha 1. Okay, so yeah, anyway, so this point onwards it makes the same changes with this alphas, but the first thing is it just consumes this A, and so then this becomes epsilon, right? And then the state changes to something, and this looks very complex, right? It is kind of, it contains this Q1 and also this subscript V1 up to BK, so lots of symbols, but this whole thing in this square bracket, so this is just the name of one state, okay. We are just naming the state with this very complex level, but this is just one level for one state, right? And from this state we will make epsilon transition, because we cannot consume any more symbol here. You see, there was only one symbol that we consumed, so we cannot consume any more symbols. So from this point onward, we will just make epsilon transition. So that will, what will that do? That will change the state, and that will also modify the stack. And how is the stack modified? So I already said, the stack is modified in the same way that happens here, right? So the leftmost symbol of A alpha 1 is replaced by something which makes it alpha 2. So the same replacement will be done here, and from alpha 2 also the same replacement will be done here, so that the alpha 3 here matches with alpha 3 here, up to this alpha k and up to this alpha k plus 1, which is beta, okay. But what about the state? So you see, what is the state? So this is Q1 and then B1 up to Bk. So everything here is a subscript, okay, of this Q. So this is just a name. So again we have another name here. So here it is 2, and then from B2 to Bk. So what will be the next thing? So Q3 and then B3 up to BK, Q4, B4 up to BK. So finally, so you see that one by one these symbols are decreasing. So at this kth step, we will have a QK and everything here is gone, only the BK is left. Okay. And then finally, even this BK will be gone. So this is again a epsilon transition. So this is only changing the state and this stack. So from this point onward, it will, here it will be QK plus 1 comma epsilon. So again, these are just names. Okay. But we need this many states in them. So this will be our new states that we introduced in M prime. You see. So we said that we have the states of this machine here. So we have this Q and P here, which is equal to these states. Okay. So we are kind of renaming this state, you can say. In fact, here, so it just moves from here to here. We have all these new states labeled by this complex looking labels, but these are just states. So we have all these new states in M prime. And we include the transitions in M prime. So the delta for M prime is designed so that it makes these transitions. And you see that this part here is being simulated by this subscript of this state, right? So this is just a small trick where this remaining input thing here. So first of all, you see that upon seeing A, it kind of first computes this H of A. So this B1 up to BK. So this is just this HA. So somehow this PDA kind of computes this HA and remembers this as part of the state, right? So the state is a mechanism to handle a finite amount of memory. So you remember that both in FA and both in PDA, the number of state is finite. So that is finite memory. So the infinite, the potential unbounded or infinite memory that the PDA has is the stack. But here, even in this finite memory part, so which is handled by states, so it somehow computes this HA, okay, and remembers this thing. So you can think of this as a sort of finite buffer, okay, a buffer space in its finite memory. So that is just an interpretation. So here by the definition of PDA, here everything is defined, but we can interpret this part as sort of a finite buffer memory, and then it kind of reads the symbol from this buffer memory without reading any input symbol, because it has read this one. So it reads the symbols from this buffer memory and accordingly make changes to the stack. Okay, so that after all this step that it took from alpha 1 to go to this alpha k plus 1, so it makes the same chain of moves to go from this stack string alpha 1 to alpha k plus 1. Okay, and then it exhausts all the symbols here that it computed, and then finally it goes to this state P. Okay. So now if this is the intended behavior for M1, then what should be the transition? So now it is easy to figure out the transition, right? So, okay, so this is what we want. So that means from Qi to Qi plus 1 in M, so which was accepting this L, so which was accepting this H, which was processing this HA, right? So for this, so somewhere here from Qi to Qi plus 1, this is what happens. So it consumes this Bi. So for this Qi, it consumes this Bi. So on Bi, the input symbol Bi, it moves to this Qi plus 1. And say the leftmost symbol of this alpha I. So the leftmost symbol of alpha I is Z, and that is being replaced by some gamma, right? So that means if this alpha I is some Z, say alpha I prime, so then this alpha I plus 1 will be this gamma alpha I plus alpha I prime. So I'm saying if somewhere here you have this alpha I is equal to say this say z alpha I prime, say alpha I prime. So then the alpha I plus 1 that you are getting in M, so this is just gamma alpha I prime, right? So this is what alpha I plus, and this is completely determined by this part, this substitution in the stack, right? So we will make the same substitution here. Okay, so if this is a move, if this is a transition in M, so we will include transitions in M prime. So we will design the transition function in such a way that it has this transition, which makes this same replacement in stack. But then this consuming of bi here will be handled by change of state here. So this change of state kind of simultaneously tackles the fact that here the state is being changed from qi to qi plus 1, and here it is consuming bi. So from the subscript we are removing this bi, and this is the new state. So this is the label for the new state, and all this form of states. So these are new states in M prime. Okay. And you see that by introducing this sort of new states, still the set of state is finite in M prime, right? That is important, because in PDA, the set of state should be a finite set. And it is finite because what are this? So you have the first thing as some qi, and the all possibilities for qi is finite. And then after this, you have a finite length string, because see, this is some HA, right? For some symbol A in sigma. So you take the longest HA for over all A, right? So that will be this. So that is still finite, and you are considering all the sub string, all the suffixes of that also. So so instead of b1 you are starting with bi. So everything here, all the possible things here are also finite. So all the combinations, if you take all the combinations of qi and bi up to bk, where b1 up to bk is ha for some a, so all the possibilities here are finite. So we are introducing this finitely many new states, and we are including the transitions for the states like this. Okay. And this ensures that okay, so and for the first step, so going from here to here, we make this. So it consumes this A, right? So these are epsilon transitions. So after this, and again, these are all kind of single step transition, you can say. So these are all single step transitions. So we do not have this stars here. So in the very first step, it consumes this A here, and from this Q, it goes to this state, which says that, okay, this is Q1, and then this here we have this HA. So somehow it computes this HA and remembers this as a part of the label of the state, right? So this transition is also here. So we can formally write down the delta for H inverse L. So it will look complicated, but it will just express this thing, that if you have a transition of this form, if you have this transition here in M, then you should have all these transitions in M prime. So that is how you construct the transition function for this M prime, and the states are same. And since we are considering acceptance by final state, the final states are same, and that makes sense for M prime, because all the states here are also states here, and the final state will be a subset of the states here. So we will use the same final states for M and M prime. States are defined, stack symbols are what? Stack symbols will be same. So the stack symbols here are same as stack symbols here. So and the Z0 here will be the Z0 here, the Q0 here will be the Q0 here, right? So everything else will be same. Only this transition function and this extra states you should take care of. And this proves that CFLs are closed under inverse homomorphism, right?